Alright, so in this video we are going to be explaining another important article about model editing. Just like previous video, again we are using it for graph neural networks. And the title of this paper is GNNs also deserve editing, and they need it more than once. Suppose a self-driving car is crashing into pedestrians, or chatbot is instructing its users to conduct criminal wrongdoing. The stakeholders of such products will undoubtedly want to patch these catastrophic errors as soon as possible. So these are hard examples that should be fixed as soon as possible. You don't need to retrain everything, you just need to fix for these catastrophic samples. So to address such concerns, model editing, the study of efficiently patching model behaviors without significantly altering their general performance, has seen considerable activity with hundreds of editing techniques developed in various domains such as computer vision and NLP. However, the graph learning community has objectively fallen behind with only a few graph neural network compatible and just one GNN specific model editing methods available, where all of which are limited in their practical scope. We argue that the impracticality of these methods lies in their lack of sequential editing robustness, the ability to edit multiple errors sequentially, and therefore fall short in effectiveness, as this setup mirrors how errors are discovered and addressed in the real world. In this paper, we delve into specific reasons behind the difficulty of editing GNNs in succession and observe the root cause to be model overfitting. We subsequently propose a simple yet effective solution, CGNN, by leveraging overfit prevention techniques in a GNN-specific context to derive the first and only GNN model editing method that scales practically. So simply classifying outputs to a degree of correctness is not enough, since two wrong outputs that appear the same on paper can result in drastically different impact in the world. And editing techniques often carry great practical significance due to their relevance in model development and maintenance. So GNNs are intrinsically less robust to editing influence due to neighborhood aggregation. Of course, this is why we don't see many papers of using model editing for GNN, because if you change just one of the nodes, then the aggregation process, when you go to layer L plus 1 from layer L, when you want to move, then even changing one of them has significant effect. That's why it's not straightforward. You need to change the problem. So that's why they have this idea. So in this work, we reveal that the main reason that GNNs are editing sensitive is not solely due to neighborhood aggregation, but lies more in simple overfitting of editing targets. So the task paradigm is like this. Suppose a GNN model M0 trained with training dataset is evaluated and test dataset. So let us assume that the evaluation results of the output, your test, indicates the model is generating undesired outputs on this E1, where X and Y are just features and labels. Label of E1. And if E1 is considered edit worthy due to E stands for edit. So if E1 is considered edit worthy due to its potential high profile impact it entails, E1 is considered the editing target at hand. So we would like to perform the editing operation upon a an editing target. Now suppose this edited model is producing another high profile error, E2. We should ideally have M2, where M2 is just Y of edited 1 and edited 2. And given that editing targets likely only take a negligible portion of total dataset, and we formalize the task objective for model editing. So we would like to have this edit for m and n-1, the n-1's edit, such that their test is similar for all edits. And n denotes the number of the nth number of editing targets. So we have some evaluation criteria: success rate, indicating the edit operation is successful; test drawdown. This drawdown comes from financial systems. This is a good measure in financial systems, like in Forex and any financial network, indicating the gap between the pre-edit accuracy and post-edit accuracy. Again, suppose we have edit of m sub I minus 1 to be m sub I. The test drawdown is the accuracy of m0 minus accuracy of m sub I. However, such criteria can get complicated under a sequential context. I mean, first we edit 1, then we edit 2, edit I plus 1. So you see, you cannot generalize this idea. So under a chain of successful editing, it is possible to discover that this happens, meaning the later edit operation has overwritten a certain previous edit, causing the current edit model to produce wrong output on a supposedly already patched instance. So to provide a faithful evaluation of the model, we utilize I's edit test drawdown and I's edit success rate. But are neighborhood aggregation and model editing absolutely incompatible? So although EGNN makes it valid and natural case that neighborhood aggregation causes GNNs to be intrinsically less robust than architectures like MLP, whether or not there exists a way to make a vanilla GNN model perform better under editing tasks remain largely unexplored. So we inspect EGNN procedure along its undesired sequential edit results, where we notice EGNN is essentially doing gradient descent toward just one particular edit target during each of its edit operations. So we suspect this might be a recipe for overfitting, or even the largest node feature we tested only has a dimension of 6,000. So overfitting mitigation helps editing robustness. The proposed architecture is like this, that we have a frozen GNN and we have an active MLP. But because it is frozen, we don't go there, only we backpropagate through this line, this path. So to edit and any target, for example, E sub I, we form an editing batch consisting of 4 types of components: the current editing target, EI itself, previous editing targets, and EI's neighbors that happen to be in train, and randomly select training samples from the train set. So given that an edit target, a set of previously edited samples and a training samples, then we initialize edit batch, then we append previously edited targets to the current editing batch. Now we get the set of all k hops of the edit target. Then we randomly select, because this is just what we get is mix-up selection, and that's it.